Okay, so now I want to do something more and try to see whether this connection with the between stochastic dynamics and quantum mechanics in imaginary time is actually deeper than we just looked at. So let me do one thing and expand the exponent. So let me once again write my conditional probability as a path integral with my path. And then in the exponent, 1 over 4d integral over time. And for the time being, is convenient not to use the discretized version until it's absolutely necessary, as we should see. So what we're going to do is simply, solve this square. And then if we do that, we get an integral from x naught to xf in dq exponent 1 over 4d integral in dt and d2 or t prime, which is probably easier to write. And then I get q dot square. I get d squared over kt squared grad u squared. And then, of course, I've got plus twice q dot and grad u integral 0 t dt prime. Oh, yeah, fine. Let's do this. So it's here I get negative 4d. So let me say 1/2 d. And there's a factor d over kt squared. So I'm just multiplying this factor here. So I get twice d divided by kt. Yes, d divided by kt. So all in all is 1 over 2 kt. Now, please stop me if things are not getting clear. Let me concentrate on this guy here for a moment. So let's look at this guy. I get 1 over 2 kt. Well, let's forget about the 2 kt. Let's look at the integral 0 t d tau. And then I get q dot grad u, right? Now, of course, this integral can be written using the chain rule for differentiation as a total derivative of the potential as a function of u, of q, right? Now, this is the point where I need to remember that this integral really is a sum over k. If I look at this integral here, star, and I write it explicitly, okay, what it really means is q plus 1 minus qk times d by du by dk u of qk, right? Now, this object here is actually a Ito integral. So basically, while I would be tempted to say that this guy here, so basically this is almost a fundamental theorem. So basically, this is a Ito integral, and it's an integral of a you know, a perfect derivative, but in the Ito calculus. And if you remember what we said last time, this is equal to what you would expect the result to be in the standard calculus. Look at the first line here. That's exactly what you would mean, because remember, this is Q of T and this is Q of naught, right? Apologize for not being able to fill all the. But if you remember what I just stated without proof, that in the stochastic sense and after averaging in the Ito calculus, you can demonstrate that this integral is not equal to this if Q are stochastic trajectories generated by an Ito process. It is equal to this plus d and then a Riemann integral over time, which basically is sum over k delta t, and then the second derivative. That's the Ito fundamental theorem of calculus. There was a typo in the notes that I tried to correct. And the typo basically comes from the ambiguities that you have when you're trying to write this Ito integral as a normal time integral, which it's kind of ambiguous. What the Ito fundamental theorem of calculus says is basically this part of the blackboard. If Q are generated by a stochastic process, on average, this summation here is equal to this term here. That's what the fundamental theorem of calculus says for the Ito. And that's well defined. Whether you can prove it or not, it's complicated, and I don't want to spend time. And I think I glanced through the proof once in my lifetime and decided that I was not going to learn it and teach it. But that's what I mean by fundamental theorem of calculus in the Ito form. Okay? So if you use it, then you can rewrite this term here and discover that after you apply this, then the integral in d tau from 0 to t of q dot grad u is equal to u xf negative u xi plus d times integral from t from 0 to t d tau of the Laplacian of u q of tau. So finally, combining all things together, we get the conditional probability to go from xi to xf in a time t is equal to, I'm pulling out the factors which come from the fundamental theorem of calculus, this factor comes from here. There was a factor 2 beta precisely here. Beta is 1 over kt. So beta over 2 is 1 over 2 kt. And there's a factor d coming from the fundamental theorem of calculus. If you combine it together, then the first term will give you this, and then the second term will give you a path integral. And this path integral will be in the following form. Sorry, apologies for this. I should probably shut off. How do I silence this? No, it should work. Oh, I use the Q once again. And there's an effective potential which is d over 4kt squared grad u squared negative 2 kt Laplacian of u. So what did we learn? We learned that basically the conditional probability can be written in the form of a path integral that now has exactly the structure of the quantum mechanical path integral in imaginary time. Because remember, in imaginary time, the path integral in imaginary time of a Hamiltonian will be, now this is quantum mechanics now, no longer stochastic process. In quantum mechanics, this object here will be a path integral from x naught to xf of e to the negative, I'm setting h bar to 1, right? So basically, I can rewrite stochastic dynamics as quantum mechanics in imaginary time with two important differences. The first one is that I don't have the original potential here. I have a different object called effective potential, which is derived from the potential through this transformation. So in particular, it's something that depends on the force and the Laplacian, not on the potential. So unlike the physical potential that is defined up to a constant, the effective potential has a dimension of a frequency, if you work it out, and it's not defined up to a constant. It's defined including in its absolute value, which means that it has a particular physical meaning. Okay? The second important point of difference is, in fact, the prefactor here. This prefactor here is not present in quantum mechanics. And we will discover later on in the course that this factor there has important physical implications. And I will elaborate on that further on in the course. So, summarizing once again, what we discover is this interesting, fascinating relationship or I can even write it this way. Where the effective Hamiltonian is given by negative d Laplacian plus the potential. So that's the effective Hamiltonian that is dual to diffusion. So you see, Einstein was almost right. Diffusion is almost like quantum mechanics, and quantum mechanics is almost like diffusion, but it's a diffusion in imaginary time. Sorry, quantum mechanics in imaginary time is mappable to diffusion. Now, are there questions so far?
Just one.
Okay.
So why we rewrote q dot gradient of u as a total derivative with respect to time? So did we use that
Sure.
or?
Oh, fine. Well, so to say, in principle, you don't need to, because in principle, what you could have done is to start from here, go directly here, write explicitly what this is all about, and use this. Okay? Now, the fact that I wrote it as a function of time is simply because I wanted to emphasize the difference with a ballistic system, in a smooth system, where I could have written this as a time, this is a standard difference of potential. And you have this integral when you actually demonstrate what is called the Teorema delle forze vive, which you might remember from when you demonstrate that the work done on a system is actually the difference of the kinetic energy. And you do exactly this demonstration. You get, you take your kinetic energy, you take the derivative of the kinetic energy, you get a term, right? And then by doing this, you discover, you get then you use Newton's law and you arrive basically to the teorema delle forze vive. But in a stochastic context, there is a fundamental difference which adds to the work done to the system some seemingly mysterious contribution, because what is the second derivative meaning physically? And we will discover that it has to do with entropy. So in this context, entropy begins to play a role even on dynamics. And and I want to show you why, and what is the physical meaning of the second derivative there. It's probably a little bit too technical that we need for this course, but let me do that anyway. Okay, so let's take a break for a couple of seconds and try to understand a little bit better what this effective potential really means. Let's look at the following probability. Let's take an infinitesimal time, dt, and ask the question, what is the probability that I remain in the same configuration after a time delta t? After all, why not? Okay? Now, if you apply this formula after discretization, well, immediately, if you have a single time steps, then clearly the kinetic energy doesn't contribute because the final position and initial position are the same. So when you discretize, you get x minus x, right? The discretized version of the kinetic energy is x final for one single time steps minus x initial squared, right? Divided by delta t squared. But if these two are both x, you don't get that. Also, the prefactor doesn't appear because the energy at the beginning is equal to the energy at the end. And basically everything that turns out that this is simply up to a constant e to the negative potential of x dt. So it tells you that the probability of remaining in the configuration decreases exponentially with time according to a rate that is given by V effective, which means that V effective defines the rate of escape under diffusion of a configuration. Now let's take two configurations. They have the same gradient, but very different Laplacian. So let's take a system like this. This is my U. I defined, okay, so if you compute, so let's say we are interested in this point here, okay, and I'm interested in the point of stochastic stability. Sorry, I'm interested in understanding V effective here in A and B. Now, clearly, in both cases, the gradient is vanishing, right? But in the second case, but the Laplacian is smaller here than it is here. Which basically means that the probability of remaining in A after a time delta t is divided by the probability of remaining in B after a time delta t is basically the ratio of the corresponding Laplacians. With some prefactor 1 over, oof, I think it's D D over 4kt, so that's D over 2, if I'm not mistaken, kt. Yeah. Now, so the Laplacian plays a role, and then you physically understand what is this doing. You see, in this point, there is so much entropy in this state that the system, if this is the thermal energy, which is fixed by kT, clearly if kT is very large, so large that it kills any structure, then these two quantities are really equal to 1. This ratio is equal to 1 in the large temperature limit. You don't care about the potential, essentially. But in the low temperature regime, where the typical thermal energy is small compared to energy variations, then clearly in this state, you have many states where you can diffuse to that are accessible at this energy. However, here, as soon as you diffuse away, you must come back because there's very few states available at that energy. From here, you begin to see the connection with entropy. The entropy of the state of the basin at A is much larger. And therefore, even though the energy is the same, the probability of staying in that point, the rate of escape is larger because you have more states to diffuse to. So there's some physics underneath this second derivative. And in fact, in a paper, I remember we even went forward inside, as much as you have a point of mechanical stability, you can define a point of stochastic stability. That is the point where this probability of escape is minimal, where the probability is maximum to stay in the same place. And they're normally not the place of mechanical stability. They're slightly different. Okay, fine. But that's really too technical. I don't think we need that. So I think we have under control what is effective potential means and why is it potentially interesting. But there's so many things we need to go further and explore. Well, one important implication of the discussion we have today is that it enables us to work out in a very effective way a partial differential equation that determines the dynamics of a probability distribution in stochastic processes. So remember, we introduced this dynamics directly from the Langevin equation. And then we say, okay, this stochastic process basically is defined in terms of a probability density that depends on time. Okay? Now, I can either solve, microscopically the stochastic differential equations for longer and longer time, then I will get my evolution by sampling this distribution. But then we discover a connection with the wave function and quantum mechanics. And in quantum mechanics, what you actually do is not generate these stochastic processes, is actually solving the Schrodinger equation. That is equation that directly tells you the dynamics of the probability distribution, or the amplitude in quantum mechanics, to be more specific. So the question that you might ask yourself is, dp by dt is equal to what? There will be a differential operator. Let me call it H, and let me add Fp for reasons that will become clear in a moment of P. I have done two things that without loss of the generality. I have put a negative here just to make it look like a negative, like a Schrodinger equation in imaginary time. And I've added the operator that sits on the right hand side. I call it HFP, but I could have called it O or whatever. It's something that, transforms a differential operator that acts on the probability. And our goal is to find out what it is. Now, what I'm going to propose to you is a highly erratic and non-conventional derivation of this equation, which you won't find in textbooks, because in textbooks you normally approach this problem of computing this equation and identify an equation from the point of view of theory of probability. I decided this way because it's more physics-based, and I think it's more illustrative of the connection with physics. Because you see, at this point, we know how to work around this problem, because we know that we have a probability. We know that we have written the condition of probability. We basically have already solved the problem. We have written the condition of probability as two terms and then a propagator, a Feynman propagator in imaginary time. Right? If you scroll back your notes, you will find out this equation, and this is my K, xf, t, xi. Okay, which basically means that I can perform the following transformation of my condition of probability. Okay. Now, this equation is particularly inspiring because if I regard this as a matrix element and this as a matrix element, this is a non-unitary transformation. You see, it's a transformation that acts on left and right. When you transform a matrix with a change of basis, for instance, right, you do something like this, right? So what this exponential factor do, they basically implement a non-unitary transformation on your propagator. And I come back to the fact that this is non-unitary for reasons that will be related with the conservation of matter ultimately. But the point that I want to make is that if I now take the time derivative of this guy, I know the answer. Because you see, I take negative time derivative and negative time derivative. So I go negative time derivative of E beta half. Let me write UF negative UI P. I'm just collecting all this factor in once and I don't want to write over and over and over. But now I know that this negative time derivative is actually equal to what for finite time? Well, this is a Feynman propagator, right? The negative time derivative of Feynman propagator is equal to the, so if let's call this K again, right? Let me remind you that dk K is equal, well, we can write it this way if you want. Do you agree? It's the Green's function of the Schrodinger equation. Now, so if I do this, then I'm left with here. Let me, for a moment, let me not worry about initial time, the delta function. Let me put myself with final positions and initial position and final times different from zero, and I will restore them at the end. Okay, so let me not worry for the moment about the singularity, just for the sake of showing where I'm going. Then you can do things properly and worry about them later. Basically, what we are doing here we have HFP, sorry, K. Okay, are you with me, guys? So now I'm almost done, because all you have to do is to propagate through. The prefactors don't depend on time, right? So I can take them back, and I have e to the negative beta half UF H E, well, K is a multiplicative factor. Well, no, not a multiplicative factor, sorry, HK. And then I have e to the beta UIF. Well, this contains derivative with respect to f. So this is if I spell it out explicitly, this is going to be this with a d here. Now you see, now in principle, we can sit down and do this calculation. And, you know, spend 20 minutes in doing the calculation. But I think you will immediately realize, sorry, I am wrong. Here is plus UI. Yes, UF, negative UF. I have to do things in the right order. Fine. You immediately realize that in the end, all these two, the exponential factors, whenever you differentiate them, they will drop extra factor, but you will still keep this. So basically, if I say take the derivative of e to the beta half ui, I will get beta half grad ui, but I will still get beta half ui, right? So this means that even if I get this derivative to act here, these two terms will still combine at the end of the calculation to form something like okay? So at the end, you will get an equation that contains negative dt of p, a bunch of terms which come from doing the derivatives, and I'm not going to do it now in this lecture. You find the notes, you get all the things done, or you can do it yourself. Okay? And then you get your p. And now it's time for me to write whatever is in here. So this is my famous HFP. And if you want now, I can write this in the conventional form. That is dTp is equal to d grad plus beta grad u grad plus beta Laplacian u p. And this is called, in many ways in the literature, sometimes it's called the forward Kolmogorov. Equation. Sometimes it's called the Smoluchowski equation. And sometimes it's called the Fokker-Planck equation. And the differences depends if you're a mathematician, if you're a physicist that lived in the USSR part of the world, or if you're a physicist living in the US. I hate to say that we were in the USA part of the world during the Cold War, but you get what I mean. So these results were discovered independently and refer to scientists belonging to their own cultural. Nowadays, we tend to call this the Smoluchowski and the Fokker-Planck the corresponding equation for underdamped limit, which includes velocities as well. But it turns out you can derive the Fokker-Planck in a completely more general way, and in the notes you find all sorts of derivation. I think I have 3 independent derivations of the Fokker-Planck equation. And I usually teach this one because I find it the most weird and interesting, connecting quantum mechanics and stochastic diffusion. Probably from the purely didactical point of view, is not the most sensible thing to do, but I enjoy it so much that, hey, I get to decide what enjoys most when I lecture, and you get to take it. Okay? So here is, I let my knowledge in quantum mechanics do the job rather than me having to learn a lot of probability, which probably would make sense for you because you would learn probability. And this way you don't learn much because you already know Schrodinger equation. But hey, fine, that's what it is. So this is the equation. It's called the Smoluchowski equation, and it's basically the equivalent of the Schrodinger equation for the probability density generated by a stochastic process. I want to emphasize that this equation applies to the original Langevin dynamics, and the Langevin dynamics defines a process called Markovian. We are assuming Markovianity here, and Fokker-Planck equations or Smoluchowski equations are deeply rooted into the assumptions of Markovianity. A Markovian process is a process for which x at time I+1 depends only on x on I, and not, or say, on x on I minus 1. So for you to be able to generate a Fokker-Planck equation, you need your theory to be Markovian, and the Langevin dynamics that we defined in the overdamp limit is in fact Markovian. Okay? Now, I just finished saying that the Fokker-Planck equation is also referred to the equivalent process in the presence of acceleration, remember, under damp case. Well, now that is clearly a case that is not Markovian in the strict sense of configuration space. Right? However, it is Markovian in phase space. What do I mean? That I can write the Fokker-Planck equation in the underdamped limit in this way, right? And now, clearly, these momenta and times are defined only at time t, in a single time. So in phase space, the underdamped dynamics is a Markovian process. So the corresponding Fokker-Planck equation will not be for the proposition only, but for the position and momentum at time t. Therefore, for a point in phase space. So in the underdamped limit, I will get an equation, which I don't bother writing exactly here, but with an operator here. What kind of structure does this remind you of? Have you already seen an equation like this for the probability in phase space? People from physics, I want an answer. Have you ever seen an equation for the dynamics of the density of states in phase space?
Could it be, well, no, Boltzmann transport equation, but it has total derivative on the left?
When you start, one of the first topics in the course of statistical mechanics for physicists, remember, you start from the Hamiltonian dynamics and you derive the famous, but before you define an ensemble, what is
maybe Liouville
the Liouville equation?
Exactly, that's not by chance that I put an L there. So this is not a Liouville's equation. The Liouville's equation is the equivalent of this for Hamiltonian dynamics. So the Fokker-Planck equation in the underdamped limit is a generalization of the Liouvillean equations for a system that is coupled to a bath. One of the fundamental properties of the Liouville equation is that it defines an incompressible fluid. Remember, So basically, the Liouville's equations can be written as a total derivative, and the total derivative, if you remember, comes from the fact that your system conserves the number of particles, right? Now, here comes a puzzle for you. We have said that the Fokker-Planck equation is basically Schrödinger equation in imaginary time. And now I challenge you saying, but the dynamics in imaginary time is certainly not unitary, right? Because the evolution operator is no longer e to the I negative IT, but is actually e to the negative HT. So if I ask myself, what is the probability in quantum mechanics of observing my particle in any point in space as a function of the imaginary time? Well, this is, of course, the wave function squared, modulus squared, integrated. Now, if I differentiate this with respect to time, well, there are many ways you can do that, actually. Fine. Well, one way to do that, you can write this as a square modulus of a propagator integrated over the initial condition. So, okay, fine. I'm getting a little bit confused in here. So let me do things carefully. So this is going to be, so let me, okay, what I'm trying to say is that dynamics in imaginary time does not conserve the total norm of the wave function. Okay, that's all I'm trying to say. And that's clear because the operator is non-unitary. But if I want to show this explicitly, let me see. I will write this as the square modulus of the probability. And then I'm improvising, so forgive me if I will take a little longer, but this will be integral in dy. I will get my propagator. I will get my initial wave function, which I assume to be normalized. Okay. And now, you see, the point that I'm trying to make here is that if I write this, this guy here, sorry, I write it as a propagator, I can use a spectral decomposition, insert a, my resolution over the identity, and this will be xn and y e to the negative en t. And now you see, when t grows, this term dies exponentially. As a result, the entire propagator goes to 0 exponentially. Right? So, in the end of the day, dynamics in imaginary time is non-unitary. So there's something missing here, because we have an equation for the probability that is sampling a stochastic process where particles do not disappear, and we map it into a quantum dynamics in imaginary time, which is non-unitary, therefore does not conserve norm of a wave function, and therefore the probability. So is there a contradiction there? Do you see my problem? And the answer is, of course, no, there's no contradiction. Otherwise, I wouldn't be teaching you. And it turns out that this is indeed a particular Schrödinger equation in imaginary time, but it's not any equation in imaginary time. It's a very, very, very specific one. How do I know? Well, because I know, because I can take my Fokker-Planck equation and rewrite it as a divergence of a current. So what happens anytime you have a, actually you should write it this way, negative d here, that's the divergence. So what happens whenever you have a, what kind of equation is this? It's called a, in physics, continuity. And normally when you have a continuity equation, you have a conservation of a global number, right? And the quantity that is conserved is, of course, the integral of the probability in this case. So this means cont, the continuity in equation, means that the norm of the probability is actually not changing with time. So summing up what we just finished saying is that, yeah, the Fokker-Planck equation is defined in terms of a non-unitary differential operator, the Fokker-Planck operator. But such a non-unitary differential operator is not any non-unitary differential operator. It's a very special one. In fact, it's so special that I can write it as I can write the Fokker-Planck equation as a continuity equation. So it's a non-unitary operator that still defines a conservation. So the non-unitarity basically is involving the breaking of time invariance, irreversibility. Dissipation always goes in one direction. I can only thermalize a system spontaneously. I never dethermalize a system. You never get your coffee at room temperature all of a sudden getting ready unless you use to be drunk hot, unless you put it into microwave or on the oven or on your fire. So that's where the unitary character of the Fokker-Planck equation goes in breaking time invariance. Nonetheless, probability remains constant, the norm, the number of particles, and you can see that explicitly in the fact that the Fokker-Planck equation can be recast in the form of a continuity equation. Now, the Fokker-Planck equation is one of the fundamental equations of physics. In the next lecture, we will continue looking at these equations. But maybe since I might still have 5 minutes, I can do two things. I can take questions, and if there's no if there is no question, I'm going to make one last statement. Are there questions? So if there are no questions, let me just make this simple statement here. Let me rewrite the Fokker-Planck equation. Now, we came to this equation from the Schrodinger side, right? So we mapped the path integral into Feynman path integral, and then we knew the equations that this Feynman path integral was obeying, and then we used this information to derive on the Schrodinger, the Fokker-Planck equation. Okay, that's the way we arrived to this. But of course, we can go either ways in mathematics. We can decide to do whatever we want. In particular, the opposite way was to say, Mr. Fokker-Planck equation. This is the Fokker-Planck equation. You derive it or you assume it, whatever. I can transform it into a Schrodinger equation by making the following functional change. So if you do this, and and you plug this back, you get an equation for psi, right? And the equation for psi is, of course, the Schrodinger equation. Now, if you look at this equation, what this equation is telling you, now, this operator, the effective Hamiltonian, is it Hermitian or not Hermitian? What is an Hermitian operator? Okay, I got it. Questions for you for next time. And then we pick it up from there. I think I bowled you already. Enough for today. So come with an answer to this question. And come with questions. Or else I'll go. See what I mean? If you don't come with questions, I move forward. So you better come with questions. Ok. Bene ragazzi. Ci vediamo giovedì. Saluti.
A giovedì,
Sì.
buona serata.